In today's lesson, we are going to talk about functions, domains, and range. You have seen so far that expressions can be written as the relationship between two variables. For instance, to give you a couple of examples, let's say y is equal to 2x minus 5, or x squared plus y squared is equal to 10. These are examples of mathematical expressions which relate two variables, y and x. This is what we call a relationship. Now, the relationship can be represented either using ordered pairs. For instance, this is an example of an ordered pair, let's say 1 and 5, 3 and negative 1. This is one example that I use the curly bracket and brackets to show that if the first number is x, the second number is y. This represents that when x is 1, y is 5. When x is 3, y is negative 1. Or it can be using tables, using table of values, x and y. I can represent this ordered pair as 1, 5, 3, and negative 1. Or it can be a graph. For instance, in this case, when x is 1, y is 5, so this is 1 point. When x is 3, y is negative 1, so this is going to be the second point. Or it can be an equation, something like these two equations that we had before. Now we are going to define a new term that you used to use before without even knowing the meaning of the term. The term is called a function. Now, what exactly is a function is very simple. We are defining a function to be a relationship, first of all, between two variables, independent and dependent. Remember that by convention, we call x to be independent, y to be dependent. Now, we define a function as a relationship where the relationship between the independent and dependent variable is such a way that for every value of x, we get exactly one value of y. So for every x, you get exactly one value of y. You do not get another y, let's call it y sub 2. This is not a function. A function is only a relationship when for every x you get only one y. It doesn't mean that it has to be the same for y too. This means that you can have a function where for every y you get two x's. It doesn't matter. Now, knowing this definition, not all relationships are functions. The question is that how we can distinguish functions. If I give you a relationship, how you can tell me by looking or analyzing that if it is a function? The technique is very simple. To see if a relationship is a function, we use what we call a vertical line test. A vertical line test, it simply says that draw a vertical line parallel to y-axis, perpendicular to x-axis. If this line cuts or intersects the graph only in one point, we call that relationship to be a function. If it's more than 1 point, then it is not a function. It is just a pure relationship. give you a couple of examples here. For instance, if I have a graph of a line which looks like this, if I draw perpendicular lines, you can see that our lines crosses the original line only at one point. So this is a function. If I have a parabola which looks like this one, if I draw perpendicular lines like this one, it crosses the graph only in one point, so this is a function. But now consider the following example. If I have a graph like this one, if I draw a perpendicular line, you can see that the graph crosses, the line crosses the graph at more than one point, so this is not a function. Another example of a relationship is a circle. If I draw lines perpendicular, you can see that the intersection points are more than one. So this is not a function also. Now, this is when you have a graph. What about if we don't have a graph? If we just have the definition of the function. For instance, let's say I have a relationship between x and y given by 1, 5, 2, 3, and 7, 8. Definition says that this is a function if and only if for every x you have only one y. To see if this is a function, it's very simple. Just look at the x coordinate of the definition here. If you can find a case that more than once an x value is repeated, then this is not a function, this is a relation. You can see here you have 1 here, you have 2 here, and you have 7 here. No x is repeated, so this is automatically a function. But if you consider this case, 1, 5, 2, negative 1, and 1, 7, then you can see that 1 here, 1x, and this x, both of them are the same, so this is not a function. In our first example, we have been given a graph. We are supposed to use the vertical line test to see if it's a function or not, and then justify our answer. For this line, you can see if I go ahead and draw vertical lines, the vertical lines cross the line only in one point. So this is a function. In the second example, you have a graph given here. If I draw the vertical lines, you can see that it crosses the graph at more than one point, as I'm showing, so we can say that this does not represent a function. In the next example, in this parabola, again, I'm going to draw vertical lines like this, and you can see that the intersection point is only 1, so this represents a function. In this example, if I use vertical lines again, the graph is cut in more than one point, these 2 points, or these 2 points, or these 2 points, so we can say that this is not a function gain. Now we are going to define a new term called domain, which is very important. Domain is all the values which the independent variable, usually x, they can take for a function. For instance, give you one example. If I give you a graph like this one, we know that by definition, this is x, this is y. The values that the x can take for this function are all these points here. For instance, for this point, the corresponding y is here. For this point, the corresponding y is here. For this point, the corresponding y is going to be here. For this point, the corresponding y is going to be here. So our x values, they start from left, negative infinity, and they go to the right, which is positive infinity. There is no restriction on the x values. So we say domain is all real numbers. And remember, real numbers are all integers, decimals, repeating decimals, all numbers. So there is no restriction or on our domain here. This is what we call the domain of a relationship. Very important topic. The next term we are going to define is called the range. Exactly the same way, the range is all the possible values of the dependent variable, which is usually we call y, for a function. For instance, in the previous example, if you can see that your y values, for any y values, I can get another x values. Now, there is no restriction on the y values which are on the y-axis. So that's why we say the range is all real numbers. Just remember that this domain and range for this example of a line is all the real numbers. But depending on the graph, there is going to be a restriction on the domain and range, which you're supposed to find either by looking at the graph or by looking at the expression. Now we are going to go back to our main topic of the lesson, which is a function. And remember that for a function, we said that for every independent variable, value for the independent variable, we have to have a unique dependent variable, value. Now, for a function, for each given element of the domain, which is the x value, you must have exactly one element in the range. If you have more than one element, then this is not a function, it's just a relationship. In this example, we have been given a relationship and we are supposed to find the domain and range. Now, this relationship for the domain, look at all the x values, which are the first numbers in the ordered pair. And write down all these x values and make sure that there is no number repeated. So I'm going to say the domain is, I can write with a curly bracket, -3, 5, -2. And since 5 is repeated, I'm not going to write it again, comma 6. For the range, I'm going to do the same thing for the second number. The first one is 4, then -6, then 7, then 3, then -8. So my domain is -3, 5, -2, 5 is already repeated, and 6, and the range is 4, -6, 7, 3, and -8. In this example, we have been given a table of values and we're supposed to find the domain and range. Again, the domain is the possible x values, which is the first column, and the range is the possible y values, which is second column. So if you look at the table, we can see that the domain is equal to 4, 5, 6, 7, 8, 9, 10. So I'm going to write it as 4, 5, 6, 7, 8, 9, 10. I'm going to write individual numbers. Do not write 4 to 10 because this means that 4.5 is also included. But if you look at the values for x, these are discrete values. So you have to write 4, 5, 6, 7, 8, 9, 10. And the range is the same: 8, 12, 5, 22, 14, 9, and 11. Now, if we wanted to decide if it's a function or not, you can see that the domain here, all the x values are unique. There is no repetition, so we can say that this is a function. We are going to define a new term called real numbers that you have already heard before, and probably you have an idea what exactly is a real number. We use the real number, and the notation for real number is very important. Is we are going to use the capital letter R to be the set of all integers. And you know what are integers? All positive or negative numbers including 0, which are not fractions or decimals, like 5, negative 3, and so forth. Terminating decimals like 1.5. Repeating decimals with the decimal digit to be repeating, for instance, 1.66666. Non-terminating decimals are numbers that they are in decimal form, but the digits do not terminate. And non-repeating decimals, opposite to repeating decimals. All these numbers, put them together, which is going to be real numbers. So real numbers include all the possible numbers, and we use R to denote them. Now, we have talked about ordered paired graph, how to detect if it's a function or if it's a relation, and how to find the domain and range of those. Now, what about if we have given an equation of a relationship? How can we determine if it's a function or relation and domain and range? The only possible way is to analyze the function, the relationship, and then based on our result, we have to decide if it's a function, relation, and what are the domain and range from analyzing, the equation. And we are going to do a couple of examples just to get an idea how this is done. Okay, in this example, we are supposed to find the domain and range of 2x minus 5 and then sketch a graph. Now, the equation is in the form of y is equal to 2x minus 5. To find the domain, you have to find the restrictions on the x values. And to find the range, you have to find the restriction on the y values. If you look at this equation, y equal to x minus 5, to find the restrictions are usually either when the variable is in the denominator or under the square root. Give you one example. For instance, if I have 1 over x, this relationship is valid as long as x is not 0, because number divided by 0 is not defined. So the restriction is everything except x equal to 0 for this example here. Or if I have something like x under the square root, since square root is defined only for positive numbers, then it means that x can take only positive values. So your domain is going to be greater than or equal to 0. Now, going back to our example, y equal to x minus 5, x is not in the denominator and x is not under the square root. So we can say that the domain is equal to any x value in real number set. There is no restriction on x. Now, to find the range, we have to find the restriction on x. The easiest way is to solve this equation for x. So I'm going to move this one to the left. So I'm going to get 2x is equal to y plus 5, and x is equal to y plus 5 divided by 2. Now the range, we have to see if there is any restriction on the y value. Since y is not under the square root, or it's not in the denominator, there is no restriction on the y value. So we can say that r is equal to y, which is a member of real numbers. Now if I plot this one, then you know that the graph is going to look like a line, which is shown here. Now if you look at the x values on the x-axis, there is no restriction on the x coordinate, because for every x value I'm going to get a y value, and the same is true for y coordinate, which is the range. So the domain is x, a member of R, and range is also y, which is a member of R. In the next example, we have y equal open bracket x minus 1 squared plus 3. To find the range again, we look at the x variable. Since x is not in the denominator and x is not under the square root, we can simply say that the domain is x in R. There is no restriction on x. But to find the range, we are going to solve the equation for x. So we are going to move 3 to the left. We're going to get x minus 1 squared is y minus 3. We take the square root of both sides, but remember, when you take the square root, it becomes plus or minus. So x minus 1 is equal to plus or minus square root of y minus 3. So x is, when you move negative 1 to the right, becomes 1 plus or minus y minus 3. Now to find the range, you can see that y now is under the square root, and since the values under the square root has to be positive, you can see that y minus 3 has to be greater than or equal to 3, greater than or equal to 0. If you move negative 3 to the right, we get that y has to be greater than or equal to 3. This specifies our range here. So we say that range is y in R, and y has to be greater than or equal to 3. Now, if you remember from grade 10, you know that this equation is in vertex form, and the vertex is at 1 and 3. And since a, the leading coefficient, is plus 1, parabola opens upward, so the vertex is a minimum point, and it specifies that 3 is the minimum value for y. So y has to be greater than or equal to 3. If we plot this one, then we're going to get a parabola which looks like this one. This is the point 3 here, and this is point 1. And you can see that y has to be greater than or equal to 3. In this example, y is equal to 1 over x plus 1. Again, to find the domain, we are going to look at the variable x, since the variable is under the, it's in the denominator, and division by 0 is not allowed. Then we are going to say that x plus 3 cannot be equal to 0. We move 3 to the right, we get x cannot be equal to negative 3. So automatically our restriction is x can be any number except negative 3. So our domain is x, a member of R, and x cannot be equal to negative 3. Now for the range, we are going to solve for x. We are going to write the equation as y over 1 is 1 over x plus 3. Cross multiply, 1 times 1 is 1, and x times y plus 3 is y times x plus 3. Now we are going to divide both sides by y. We're going to get x plus 3 is equal to 1 over y, or x is equal to, if you move to the right, 1 over y minus 3. Now, we are going to look at the restrictions on y. Since y is in the denominator, we know that the denominator can't be 0, so y cannot be equal to 0. So our range becomes y, a member of R, and y cannot be equal to 0. Now, if you go ahead and plot this function using table of values, which we are going to cover later on, how to plot functions with the variable in the denominator, which is rational functions, you are going to get a graph like this. Now this line is x is equal to negative 3, which was our restriction. This line is called x equal to y equal to 0. Now these two lines, x equal to negative 3 here and y equal to 0 here, they have a special name. We call them asymptote. These asymptotes are lines that the graph gets close to it, but it never hits or crosses their line. So our function has two asymptotes. One is a vertical asymptote, which is x equal to negative 3, the vertical one, and the other one is a horizontal asymptote, y equal to 0, which is the horizontal line, which is the x-axis. So remember, these two lines that the graph never hits, but it gets closer and closer, are called asymptotes. In the next example, we have y is equal to square root of x minus 1 plus 3. Since x is under the square root, and we know that the square root of negative numbers do not exist, we know that the restriction on x minus 1 has to be that x minus 1 has to be greater than or equal to 0. So moving this one to the right, we get x has to be greater than or equal to 1. So this means that the domain is x in R, and x has to be greater than or equal to 1. For the range, we are going to look at y equals square root of x minus 1 plus 3. Since this quantity here can only be greater than or equal to 0, because square root returns either 0 or a number which is greater than 0, we can see that y can go from 3 upward. So y is greater than or equal to 3. So the range is y in r and y greater than or equal to 3. Now, if we go ahead and plot this one again using table of values, we are going to get a graph which looks like this. And this value here, the y value, which is 3 here. And the x value is going to be 1 here. In the next example, we have a relationship x squared plus y squared is equal to 36. If you remember, this represents a circle of radius square root of 36, which is 6. So we get a circle which looks like this one. This is 6, this is negative 6, this is 6, this is negative 6. You can see that x goes from negative 6 to 6 and y goes from 6 to 6. So our domain is x in R and x less than or equal to 6 greater than or equal to negative 6, and our range is x, y in R and y again between 6 and negative 6. The next example is a word problem which states that Amy has to enclose a rectangular area behind a human society. Let's draw a diagram of the situation. This is one side, which is the building, so this is the building here. Now we have to enclose this area which is inside. Now we have only 100 meters of fencing. Let's represent this side to be x. This is a rectangle, so this is x. Since the whole fencing is 100, so the remaining for this side is going to be 100 minus x, which is 100 minus 2x. Now the area is just length times width, so the area is going to be x times 100 minus 2x. In the second part, it says find the domain and range for the area function. Now, the area function from the previous part we found was x times 100 minus 2x. Now, we have to look at the context of the problem. Since x represents the length, meaning this is 1, which is the width, and this is the length, we know that it has to be every dimension of the rectangle has to be greater than 0, not even equal to 0, greater than 0. So we know that x has to be greater than 0 for this case, and 100 minus 2x has to be greater than 0. To solve this inequality, I move negative 2x to the right. We get 100 is greater than 2x. Then we divide by 2. We get that x has to be less than 50. So this means that x has to be less than 50 greater than 0. So our domain is x in R and x has to be less than 50 greater than 0. For range, we are going to solve for the area function, which is this one. This one, if we make it equal to 0 to find the zeros, is going to give us two values. Either x is equal to 0 or x is equal to 50. Either x is equal to 0 or this guy is equal to 0, which is going to give us x equal to 50. These are the x-intercepts of our parabola. To find the x-coordinate of the vertex, we are going to add 0 and 50, and then divided by 2, we get 25. To find the y coordinate of the vertex, we are going to substitute this x value back in the equation. I get 25 times 100 minus 2 times 25. If we evaluate this using our calculator, we get 1250. This tells us that the maximum area, or the y coordinate of the vertex, is 1250. Now, if you expand this equation, area function, we get 100x minus 2x squared. Now, this represents a parabola opening downward because of -2, vertex at 25 and 1250. So we're going to get something like, let's say, a parabola which looks like this one. So you can see that the area can go from 1250 and it can get to 0. So our range is A in R, and A less than 1250, greater than 0.